Now that I've kind of talked about light emission, I do want to talk about something that's a little bit more real. I want to talk about incandescent lamps, and then I'll talk about the compact fluorescent lights, and then we'll talk about lasers, and pay attention to efficiency. This is your standard light bulb, or at least an old school light bulb. They're going the way of the dodo. But this is a glass enclosure, and it probably has some gas inside of it, and that's going to essentially prevent this thing from oxidizing. And what we have is we have a tungsten filament, and that's just metal, and we're going to pass some current through this thing, and as the current goes through it, it's going to heat this guy up. As it heats up, we're going to experience incandescence, and it's going to put off light. In the case of this light bulb, most of the light is put off in the infrared, and we can't see that infrared, so it's kind of defeating the purpose of the light bulb. The light bulb is to give us visible light, but if most of it's in the infrared, then lots and lots and lots of it's going to be in the form of heat, and not a lot of it is going to be in the form of visible. And I'm probably not telling you anything that you don't already know. These light bulbs, they burn hot. Now, the efficiency is about 10%, and that's not very good. This is essentially why these things are going the way of the dodo. A fluorescent lamp, or a compact fluorescent lamp, so a CFC, if you will, works pretty much the way that I told you, where we bombard this thing with some electrons, we excite some mercury, it emits some ultraviolet, it hits some phosphor, and it's going to emit some white light. And the old school ones of these that put off like the harsh industrial white light, but especially with the CFCs, we've gotten far better at what colors the phosphor puts off. The benefit of these guys is they draw less power for the same amount of wattage. We used to refer to wattage as how much light got put off, but now it's kind of like the brightness and the color, if you will. So we get less power draw for the same brightness using a CFC. So CFCs are far better in the long run, and they also tend to last longer than the tungsten. The mercury is not what burns out. The mercury can do this indefinitely. What burns out, and you've probably seen it, are the ends of this guy. Which one is more efficient? It's going to be the fluorescent lamp. Again, incandescent light bulbs are very, very, very inefficient. They put off lots of heat. The fluorescent lamp, well, you can touch those things when they're on. They're relatively cool, so they're far more efficient. Now, let's go ahead and talk really quickly about lasers. Before I talk about lasers, I want to talk a little bit about light, and let's just talk about white light. White light is going to be all the colors of the rainbow, or red plus blue plus green, and something that is kind of important is these colors don't have to be in phase with one another. And when I say in phase, I mean the peaks all don't have to line up with the crests or anything like that. Now, we actually have a special name for this. We call this incoherent light, and essentially this is going to be lots of frequencies of light, and they are not in phase with one another. You can kind of see the reds right here, you can see the greens right here, and you can see the blues right here. Notice that the blue wiggles more than the red does. Blue has a higher frequency, and a higher energy, by the way, and the green's kind of somewhere in between. But the peaks don't line up, the crests don't line up, and we get this big jumble of essentially white light. This is not laser light, but I'm going somewhere with this. Bear with me. Now, suppose I had a single wavelength. Suppose I had monochromatic light. That's what monochromatic really means. And if I were to say this light is out of phase, then I'm going to have one color of light. But again, this is going to be a peak, and this is going to be a peak. It's not lining up with other peaks or anything like that. So this would be monochromatic light, single color light that is out of phase. And this would actually be red based on, this drawing and the previous one. Now, what would happen if we were to line up the same color, the same frequency, line up all the crests like this, and line up all the troughs kind of like this? Then we would actually call this light coherent, and that means essentially all the peaks line up and all the troughs line up, and it's going to be of the same exact frequency. This would be laser light. Laser light is going to be coherent, it's going to be in phase with each other, and it's essentially going to be a single frequency or a single color. The question is how do we produce this? Well, we produce this using a laser, and again, it's going to produce a single color beam of coherent light. Now, there are many types of these guys and many applications, and we can hit we can hit lots of wavelengths. And essentially, the stuff that's inside of the laser is going to determine the color. Now, lasers are not a source of energy. You have to take a laser, you have to plug it into the wall. So it's not a source of energy, we're just converting electrical energy into light energy, kind of like a light bulb does, only actually quite efficiency. So let's just talk about lasers, and all lasers, or a bit better yet, a gaseous laser, is going to have a gas inside of a tube. And the exact composition of the gas is going to depend on the colors. And let's just talk about a helium neon laser, a HENI laser, and it puts off kind of a reddish colored light. Inside of it, there's going to be this tube, and it's going to contain about 85% helium and about 15% neon. The helium is going to be the small black dots, and the neon is going to be the large colored dots. You can kind of see these guys right down here. Now, you may be asking yourself, why is this tube full of helium and why is it full of neon? What's so special about these guys? Well, it has to do with those metastable states, the states that kind of last for a long time. So what we're going to do is we're just going to go ahead and put some high voltage across this thing. And much like the fluorescent light, it's going to excite both the helium and the neons, and they're going to start to de-excite. But helium actually has a metastable state, and this state is really important. It's going to hang on there for a while. And what's going to happen is we're going to get a bunch of helium atoms that are excited. These are the black open circles. We have a special name for this. We call it a population inversion. And they're going to bump into the neon, and they're going to excite it, which is going to excite a hard-to-come-by state of the neon. This is also a metastable state, and because they're very close, that allows this to happen. The high voltage doesn't actually excite this particular state. We're going to get a bunch of these open circles, and these are now the neon atoms that are excited. And actually, I was wrong. This is actually the population version, and we have a bunch of these guys that are waiting to de-excite. Now, something that's kind of interesting is these neons can be stimulated into being excited, and what stimulates them is just another photon going by them of just the right frequency. So lasers are actually using something called stimulated emission, and essentially that's like jumping on the bandwagon when it goes on by. So these neons are going to start to de-excite. They're going to send out a certain frequency, and all these other guys are going to jump on the bandwagon, if you will. The color is actually kind of a reddish color, and it's going to be pretty much in every single direction. What I didn't tell you is on the ends of this glass tube are going to be some mirrors, and they're going to reflect the light that's going in the side-to-side direction, and we're going to get a buildup of photons that are going back and forth, back and forth, back and forth, and back and forth. This is kind of like an avalanche of photons, if you will. They're all going to share the same frequency, the same color. They're all going to be in phase, and they're all going to be going in the same direction. So back and forth between the mirrors, becoming amplified, getting more and more and more energy every single time it goes back and forth. Again, we have a mirror here and a mirror right here. One of those mirrors is actually partially transmissive, and so they're going to say that this one right here is going to reflect 100% of the light, and this one is going to reflect not 100%, but close to it. So it's only partially reflecting, and then we're going to get this nice beam of laser light coming out. Again, it's going to be a single wavelength, it's going to be in phase, and it's going to be in a single direction.